this is section 7.5, the last section in chapter 7. We are going to be discussing exponential and logarithmic models. Now, a model in mathematics is a function or an equation that represents what is happening in the natural world. And so we're writing a relationship between and among variables that represent what's naturally occurring or what we naturally observe in the world. And so we're going to specifically talk about some exponential and growth models and logarithmic growth models that fit with the world. The first two you already know. We have exponential growth and exponential decay. In exponential growth, we have a basic y equals a e to the bx graph, and we have that same y-intercept of 1 and the same horizontal asymptote at y equals 0, and then the same exponential growth model. The second one, which we call exponential decay, is the exact same form, but your exponent, in your exponent, you will see a negative. There's a little negative in there, e to the negative bx. And that means b has to be greater than 0 if we're going to stick the negative there. But in decay, you see a negative exponent. We still have that intercept at 0, 1. But now as time goes on, as my x-axis marches on, my function, instead of blowing up like it does in this one, now decays down to 0. Okay, so those are growth and decay. We also have this model called a Gaussian exponential growth model. In a Gaussian exponential growth model, this is something that you see it's called a Gaussian model, but it's also called the bell curve. This is what people call the bell curve. And so the highest value you get to is 1, and then you have this, you still have a horizontal asymptote at y equals 0, and you have this on both sides. It's kind of like an exponential if you didn't grow or decay, but you would only go up to 1. And so a bell curve, things naturally, like averages of a test scores naturally fall under this bell curve, where you take a bunch of set of numbers and you find the average of them all. Well, so many percentage land within this x-axis would be the mean or the average of them. But that's the bell curve. Okay, then we have logistic growth. Populations do not grow exponentially. They sort of grow exponentially. They actually grow logistically. With logistic growth, you still have this horizontal asymptote at y equals 0, but you will have a second horizontal asymptote at y equals a, that top number in your function. Okay, and what happens is we have sort of an exponential growth, and I think that I need to center that. Yeah, we have sort of an exponential growth, but what really happens is there's a natural carrying capacity that the population will hold, and your population will not grow beyond that number. For example, the Earth and humans has a natural carrying capacity, and I think that they're all pretty set that the natural carrying capacity is around 13 billion people. And so we follow this exponential growth curve where A would be 13 billion. Okay, and then there's logarithmic growth. And in logarithmic growth, you have just a natural log function. And the x-intercept is now at 1, and you have the vertical asymptote x equals 0. Okay, now we have some examples. So here I have a population that I am saying is growing exponentially. So in this population, t equals 0 represents the year 2010. And the question says, when will the population reach 75,000? So in a lot of these word problems, you're given the model. So my model is population is 53,842 e to the 0.030 t. And so when will the population reach 75,000? The way you read these is you look at these numbers. That number 75,000 is a population. I'm going to put that into the spot where population goes, and the question uses the word when. And so that means I should solve for a time period. And so we're going to put in 75,000 and solve for t. So we would divide both sides by 53,842. And now I have one less number over here by my t. I'll take the natural logarithm to eliminate the e. So the natural log of this fraction, 75,000 over 53,842, that will now equal 0.03 t, and I simply divide that number by 0.03 and I will get the time. Okay, and so I have pulled up my calculator here and I have typed in the 75,000, the natural log of that ratio, and then divided by 0.03, and I have the number 11.05. So that means that t is 11.05 years. This means that the year, since this t equals 0 represents 2010, this will be in 2012 or and 22, because the year 0 is 2010, so like 0.4 would be in the year 2010, so 0.05 would be the year 2022. Okay, let's move on to the next question. All right, here we have, and this is a familiar one, we have money compounded continuously. This one says continuously. So if you're compounded continuously, then the amount you have is the initial principal amount, e to the interest rate times time. So we want to double p dollars. So we want our amount to be 2 times the principal we started with. Okay, so now I'm going to solve this for time. Okay, and I know I'm doing this in terms of all the letters. I haven't plugged in any numbers yet. That's just to make my life a little easier in the long run. So I'm going to divide both sides by p. That gives me 2 equals e to the rt. I'm going to eliminate the exponential by taking the natural log of both sides. And then when I solve for my time, I get t equals the natural log of 2 divided by r, where r is an interest rate. So I would put that in as a decimal. And so now you can fill in this column. So over here in my calculator, I want to do the natural log of 2 divided by the interest rate. And my first interest rate, I didn't see it, was 1%. So I have 1, 3, 8, 10, 11, and 12. So 1% is 0.01. And then I'm going to do 3%. So divide by 0.03. And then 8%. Oh, wait. Did I not do that? All right. And then 8%. And then I want 10, 11, and 12. Now notice this is changing by a lot. Okay, so I have typed them all in, and I want you to notice how important the interest rate is. So when I had 1% interest rate here, it took me 70 years almost to double my money. But when I had 3% interest rate, it didn't take me a third of the time. It took me less than, or 3 times as much, fewer. Well, that is about 3 times fewer. So that's 23 years. And then when my interest rate was 8%, it took me 8.6 years. And then at 10%, it only takes about 7 years. 11% takes me 6.3 years, and you will double your money if you invest at 12% in less than 6 years. You will double your money. And that's an interesting thing to notice. So I want you to take those numbers, fill them into this table, okay, and make sure you have that done. All right, next example. Here we have half-life. So remember, our half-life formula is the amount that we have was the initial amount. Oops, let me write this over again. The amount that we have, A, at time t, is the principal or or the initial amount that there was, times 1/2 to the t divided by h, where h is your half-lifetime. So here I have some sort of radioactive element with a half-life of 24,100 years, so that's h. What is the initial amount if after 1,000 years there are 2.1 grams? 1,000 years, that's the time. 2.1 grams, that's the amount at that time. So I'm going to put 2.1 in for A. I don't know P. That's actually the question, right? The initial amount is the question. So times 1/2, my amount of time that has elapsed is 1,000, and my half-lifetime is 24,100. And then I need to find P. So this part over here is just a number you can type into your calculator, and then P is going to be 2.1 divided by that. So let's see what you get for that P. Last question. Here I have a logistic growth model. This is the population of deer in an animal preserve. Okay, so the carrying capacity of the preserve is 10,000 deer, apparently. Estimate the population after 6 months. So 6 months, T, notice T is in months. So I'm just going to make T equal to 6. I'm going to find P of 6. So that would be 10,000 divided by 1 plus 90. E, and then I type in negative 0.1656 times 6. And then we're going to figure out what that answer is. And then the next question is B, after how many months will the population be 5,000? So I'm going to make the population P be 5,000. And now I'm solving for T. So that equals 10,000 over 1 plus 90 e to the negative 0.1656 t, and we're going to solve for t here. All right, I'm going to go ahead and help you solve for this. Notice the thing we want to solve for is in a denominator. I have to get rid of my denominator by multiplying both sides by 1 plus 90 e to this negative 0.1656t. So that's going to give me 5,000 plus, that'll give me 45 with 4 zeros, e to the negative 0.1656t, and that will equal 10,000. And I can now subtract away the 5,000. Then divide by 4,500. Okay, so that's going to be 1/9, 5 over 45, and then 3 zeros cancel. Now, so now I'm much simpler, and to solve for t that's in an exponential, I'll do the logarithm. I'll switch to logarithmic form. That's t. And then finally, I'll divide by negative 0.1656. And let's see what that is. The natural log of 1/9 divided by negative 0.1656. And I got 13.268 years. 13.268 years. I think that was it. Okay, so you have just a few things to do. I want you to type this in. This question here, I want you to just type this into the calculator and find the answer, and then fill out the table on the previous page, which I already did all of the math for. You just need to write it down.